welcome back. We are discussing about measurement of resistance, and the theme of this chapter is primarily the fact that measurement of low and means very low and very high resistance is not that easy. We need special precautions while doing that. So, in this video we will see what are the problems that we may encounter if we want to measure a small resistance with a Wheatstone bridge, and what is the remedy. The remedy is called Kelvin's double bridge. We will also see the principle of Kelvin's double bridge. Okay. So, let us begin. Suppose I have a Wheatstone bridge with which I want to measure a small resistance. So, the title is measurement of low resistance with a bridge. So, we shall first see Wheatstone bridge. Now, so one among these four resistances definitely is the unknown one which you want to measure. Say this is the unknown resistance, call it R, Rx, X for unknown. So, this is the unknown resistance, and all other resistances are known, call them P, Q, R and S. Okay. So, let us write P, Q, S are known, R x, x for unknown is unknown, and R x is a low resistance. Okay. Now, if R x is a low resistance, then we may need possibly another resistance which is small. Okay. Why? Because at balance we will have R x is equal to P by Q multiplied by S, and we will run into problem if any resistance is small. So, we can choose possibly say P and Q to be of higher or medium value. Okay. So, we may choose, so if we choose P and Q to have medium value, because medium value resistances are easy to deal with, because contact resistance, terminal resistance are negligible compared to the main resistance itself. So, because terminal or contact resistances can be ignored, okay. But if the resistance itself is small, then contact resistances are not ignorable. So, we may choose P and Q to be of medium value, but R x is of low value, small value. So, therefore, it is possible that S is also a low value resistance that is required to get this balance. So, it may happen that the required value of S for balance is also low. Okay. It may or may not happen. So, it may be possible that with a medium value S, this quantity P S by Q comes out to be of a low value. Then it's fine. Okay, no, not much issue. But it may happen that this is so medium by medium, it may be a medium value. So, S we need possibly a small value, so that the right hand side is again a small resistance, because left hand side is a small resistance. So, we may or may not need a small value of S to get this balanced. Okay. Okay, so let's assume that the required value of S happens to be small, is also small, also low. Thus, what we have, R x and S, these two are low value resistances. R x is definitely low value resistances, because we are measuring a low value resistance. S may or may not be of low value, but let us assume this comes out to be of a low value. And P and Q we have chosen to have medium value. If so, we have, let us draw the 4 resistances. P medium by choice, Q medium by choice, R is low, because we are measuring low value resistance, we have no choice, is assume that it also is small. Now, we have to form the bridge by connecting these 4 resistances with wires and to their terminals. So, let this be the terminals, and we connect these 4 resistances with wires like this in the form of a square, and say then we put the power supply across 2 opposite terminals, maybe these 2, and say we put the galvanometer or the detector between the other 2 terminals, which is here. Okay. So, let me just connect this. Okay, fine. So, I can connect it like this. Okay. Now, this is a low resistance, and this we assume to be low. Okay. These 2 are medium value resistances. Therefore, the contact resistance due to this terminal, which causes some resistances here, etc. So, this resistance, the small resistance can be ignored, because P is of much higher value. This also can be ignored, because P is of much higher value. Similarly, this contact resistances can be ignored, because Q is of much higher value. But here, this contact resistances, okay, cannot be ignored, because R and S are small, are low value. Okay. Therefore, this contact resistance is getting added to this actual value of R and the value of S. Say if now let us take say an example. Say R is 1 ohm, small, S is also 1 ohm, okay, and say this contact resistance here, it comes out to be say like 0.5 ohm, and here it comes out to be, so this together everything contributes to a 0.5 ohm resistance in series with R, and say here we have a 0.1 ohm resistance in series with this, okay, with S. Okay, so this side will have a total resistance of 1.1. Okay, so here 1.1 ohm, here we will have 1.5 ohm, and say at so we may get the balance at say with P equals, call it 150 ohm, and Q equals 110 ohm. Okay, so clearly P by Q is same as R, I mean R plus this quantities. So let's write 1.5 by 1.1. So clearly this is the balance condition. Now the estimated value of R, that will be given by what? This will be given by P by Q multiplied by S. The nominal value of P, nominal value of Q, and the nominal value of S. Okay, this is the nominal value, or the value marked on top of this resistance box. Okay, so this will come out to be 1.5 divided 150, P is 150 divided by 110, and the nominal value of S, we know the nominal value of S is 1 ohm, because we do not know how much these contact resistances are. We have no idea about these contact resistances. These are variable, I mean they can be anything. We have no control over these contact resistances. We know that the nominal value of S is 1 ohm. We have no idea about any of these contact resistances. So therefore, we will put the nominal value, which is 1 ohm, and this will come out to be 15 by 11. Okay, which is not same as this value of R, which is not same as 1 ohm. And this problem is due to these contact resistances. Okay. Now these contact resistances do not create a much problem, because even if we had added a small quantity to 150, like say 150.5 and say maybe 110.3, these small quantities do not create any problem, because the ratio remains almost same. So these contact resistances, beside these medium value resistances, they are not of much problem, but these contact resistances are definitely creating problem, because this actual value of the resistances, they that itself is small. Rx is small, S is small, so a small change will create a large problem. Okay. So this is the problem. So the problem is, since R and S are of low value or small value, any small addition of contact resistance will create large change in the calculation. Okay. So that is the problem. Now, if there is a problem, there should be a solution too, and the solution is called the Kelvin's double bridge. Okay. So, while talking about Kelvin's double bridge, we will divide the talk in two parts. Okay. So, we will first talk about the mathematics behind Kelvin's double bridge. Okay. So, we will first talk about the mathematics or circuit theory, whatever you call, of this bridge. And then we will talk in more detail how the effect of contact resistances or terminal resistances are are mitigated. Okay. Or how the problem of contact resistance is solved. So, these two topics we will cover while talking about Kelvin's double bridge. So, first the circuit theory, the circuit. Okay. So, the circuit looks like this. It has 6 resistances. Okay. So, the bridge looks a bit complicated, but once you understand this bridge, the function of each resistance, then you will see it is not difficult to remember this bridge. But right now, let us start with this circuit being given. Let me call this resistance as P, this as Q, this as R, this as S, call this as A, call this as B, and call this as C. Okay. So, the power supply is here and the detector is here. So, this is the bridge. Okay. Now, we need to find the balance or null condition of this bridge. Okay. What is the balance condition? When this detector will show 0 deflection. To find that, we will apply a star delta conversion in this region here. So, consider this delta A, B, C. Consider this delta and we will apply a star delta conversion. So, we will make an equivalent star circuit for this. So, let us apply star delta conversion or delta to star in this case, delta to star conversion. Okay. So, what we will have? We will have, let us draw first everything else, P, Q, this is P, this is Q, here we have the detector D, okay, and then here is the R, okay, and here is the power supply. So, okay, just one small note, at this moment please do not think why is this bridge like this. Do not think about how this bridge is obtained. Focus on the fact that this bridge is given to us and we are finding the balance condition using our knowledge of circuit theory. Okay? Do not concentrate on the question why or how have we got this complicated bridge. Do not go into that question. We will talk about that later when talking about this. Okay. Right now, this is just a straightforward circuit simplification problem. Okay. So, this is the circuit given. We are now to simplify this circuit using a star delta conversion. So, this delta, okay, so this delta part will now become a star. Okay. So, this is this A, B and C, they are converted into 3 star connected resistances. This delta becomes this star. Okay. Now, what will be the value of this 3 resistances? Okay. So, the value of this resistance, that means this branch, is given by, so this is A, this is B. So, if you recall the formula for delta star conversion, this is this multiplied by this divided by the sum of these 3. Okay. So, this branch will be A B divided by A plus B plus C. So, this will be A B by A plus B plus C. This is this resistance. This resistance will be how much? This is this branch. This will be A C divided by A plus B plus C. So, A C divided by A plus B plus C. What will be this? So, this is this. So, this will be B C divided by A plus B plus C. So, this will be B C divided by A plus B plus C. Okay. And this is S. Okay. So, this is the equivalent circuit. Now, an important fact, in this bridge, in this Kelvin doubles bridge, whenever we change any resistance, so these resistances are variable. So, you can change P, you can change Q, all these resistances you can change. Okay. Whenever you change any resistance, change it in a way such that the ratio P by Q is equal to A by B always. So, if you change P without changing Q, that means P by Q is changed, you have to change A or B at the same time, so that P by Q equal to A by B is always true. Okay. So, this is maintained. Okay. So, let me call it while changing any resistance, one must ensure this condition. So, if you change P, at the same time you have to change A, so that P by Q is A by B, or you can, if you change Q, you may change B, so that P by Q is once again A by B. You cannot change only P or only Q without changing A and B. You have to change this together. Okay. So, this is what you have to maintain while using this bridge. So, this is a condition that must be satisfied, that must be maintained. Okay. Now, so this is the equivalent circuit. Okay. So, this is the equivalent circuit of this bridge, and now you see that this bridge looks like a Wheatstone bridge. It has 4 arms. So this looks like a Wheatstone bridge. Four-arm bridge. What are these 4 arms? See, this is one arm, this is another arm, and these 2 together you can think as another arm, and these 2 together you can think as another arm. Okay, 1, 2, 3, 4. So these are the 4 arms of a 4-arm bridge. We have the detector between 2 opposite terminals, here and here, and the power supply between these 2 terminals. So this bridge is now equivalent to a 4-arm bridge, and therefore we can now write the balance condition for this bridge using the balance condition of a Wheatstone bridge, which is, so for this bridge now we can write the balance condition. So let me come here, balance condition we can write this, say P by Q, P by Q is equal to these 2 together, R plus AC by A plus B plus C, and these 2 together, S plus, so S plus this branch BC by A plus B plus C, BC by A plus B plus C. Okay. So this is the balance condition of this bridge. Okay. So now, so let us simplify. Let us now simplify this equation, and for that let us put P by Q is equal to A by B from this. Okay, we can put, because we know in this bridge we always maintain the ratio P by Q equal to A by B. So in place of P by Q we can write A by B. So let us write this as A by B is equal to R plus AC by A plus B plus C, and here we can write S plus BC by A plus B plus C. Okay. Now this will imply, so let us cross multiply the terms and see what we get. So we will get S plus this term ABC by A plus B plus C, ABC by A plus B plus C. This will be equal to RB plus BAC by A plus B plus C, BAC by A plus B plus C. Simply cross multiplication of this with this, this and this. Now these 2 terms ABC by A plus B plus C and ABC by A plus B plus C we can cancel from both sides. So then we are left with AS equal to RB, or we can write from this AS equal to RB, which will imply A by B is equal to R by S. Okay. Okay. Now, and we also know that P by Q is equal to A by B. Okay. So we can write also that P by Q is equal to A by B. This is maintained, this is carefully maintained. and A by B comes out to be R by S. So, this condition is derived, this part is derived. So, from our derivation. Okay. So, this is the balance condition for this particular bridge, Kelvin's double bridge. Okay. So, this is the balance condition. Okay. So, let me write once again, P by Q is equal to A by B is equal to R by S for Kelvin's double bridge. So, this is the essential circuit theory of this bridge. Okay. Now, let us investigate this question, how the effect of contact resistances can be avoided. Okay. So, how to avoid contact resistance problem? We will start by drawing, say, a Wheatstone bridge. So, this is a Wheatstone bridge with, call this resistances P, Q, R, S. This is a 4-arm bridge. Okay. We can have the detector here and the power supply here. Okay. So, this is a Wheatstone bridge. Now, say R is unknown and a low resistance. R is an unknown low resistance, and say the required value of S for the balance is also low. Okay. So, R is unknown, required S for balance is also low. P, Q are chosen to be of medium value. Okay. And PQ S are known and variable. So, R is unknown, PQS are known and variable, and you can choose P and Q to be of medium value, and S, suppose it is required S to be small. Okay. So, now this contact resistance is here, this can be ignored, no problem. But to avoid the contact resistances of R and S, let us use 4 terminal resistances as R and S. So, let us use 4 terminal resistance. So, we will connect it this way. So these are the 4 terminals. And we will use okay, now let me connect it here. And this here. Okay, so we will essentially use Kelvin's double bridge. And so what we will do, we will connect 2 more resistances, A and B, okay, and this we will sort, okay, and we'll connect it here. Okay, so we have started with a Wheatstone bridge and modified that into a Kelvin's double bridge, and we are using this as 4 terminal resistances. So we are using, so this is in a box, this is in a box, 4 terminals are outside. Okay, now so let's name the contacts, these contacts as call these as C1, C2, C3, C4. Okay, so this terminal can be connected maybe here or here, or maybe at like this. Then C1, C2, C3, C4, what else? C5, C6, C7, C8, C9, C10, C11, C12. Now these are the problematic contact resistances. This may be this can create some problem. Okay, so now let us analyze what kind of problem can this contact resistances create. Okay, observe that this C5 and C1, C5, C1 and C2, these are small resistances in series with P. C5, C1, C2, these are small resistances in series with P. So, and P is a medium resistance, that is a much higher resistance than this contact resistances. So, this is medium, this is also medium. Therefore, C5, C1 and C2, C5, C1 and C2 can be ignored in comparison with P, because these are in series with P and P is of much higher value. So even if you add these small resistances to P, the ratio, say P by Q, is not going to change. P by Q or P plus these resistances by Q are going to be same. So these resistances can be ignored in comparison to P. Similarly, these resistances, say C3, C4 and C10, can be ignored in comparison with Q. Q is of a larger value than these contact resistances. So you can ignore this three. Okay. And now then, so this is solved, this is solved, solved. This is not going to create much problem. Okay. Now let's see C7 and C12. Okay. So let's talk about C7 and C12. C7 and C12 can be thought of as a part of internal resistance of the source. Okay. So the source also can have some internal resistance, and we know that in our balance condition this resistance doesn't come in the equation. So this resistance C7 and C12 we can think as a part of this source resistance, which do not come in the balance equation. Okay. So they do not come in balance equation, Okay. Now, so this is solved. Okay. C6 and C9. Now C6 you can think it is in series with A. You can choose A to be of medium value. We should choose A to be of medium value, and similarly B we should choose to be of medium value. So let's write A and B are chosen to be of medium value, and such that of course A by B is equal to P by Q. So this is what we maintain. If we change A, we change P. If we change B, we can change Q, so that this ratio is maintained. And A and B are chosen to be of medium value, larger value. So C6 and C9 can be ignored in comparison to A and B. So C6 and C9 can be ignored compared to A and B respectively. Okay. So this is not a problem, this is also not a problem. So see, almost any of this 1, 2, 3, 4, 5, 6, 9, 10, 7 and 12, they do not create any problem, much problem. Okay. 7 and 12, they do not come in the balance equation at all, and other resistances, they are in series with larger resistances A, B, P, Q, so they are negligible. But C8 and C11, what about them? So what about C8 and C11? So C8 and C11, they will have some resistance. This resistance so they will have some resistance, call this call all these resistances together as C. Okay. So C8, C11, all these contact resistances together you call a one resistance, they are in series, so you can call them as a common resistance C. And you see that this is nothing but our Kelvin's double bridge. Let me zoom out and show you the two circuits. So this is the Kelvin double bridge. We have, say you see, PQRS. Between R and S we have some unknown, we have some resistance C. Here also PQRS. Between R and S we have C, and across C we have AB. Across C we have this AB. So these two bridges are exactly same. And then in this bridge, when we have derived the balance equation, okay, C doesn't come in picture at all. Whatever the value of C, it doesn't come in the balance equation. Okay. Therefore, in this bridge as well, whatever is the value of C8, C11, the contact resistances, they do not come in picture at all. So this C8 and C8 and C11 do not come in balance equation, in the balance equation. Okay, and that is so because of the principle of this bridge, this circuit. And this is actually true because we maintain always P by Q equal to A by B. If we do not maintain this ratio, then C may not get eliminated. Then C may come in the balance equation. But if we maintain this ratio, then C has no effect. And this is how all contact resistances can be mitigated. So this is the Wheatstone bridge, and once again let me repeat before I conclude that we have, these are 4 terminal resistances. If we have R and S as small resistance, we must use 4 terminal resistance. Once again, 4 terminal resistances are becoming so important, and we have to connect it in this way so that all contact resistances, they either go in series with larger resistance and their effect is negligible, or they come in this branch of the Kelvin bridge which doesn't have any effect in the balance equation. So this is the beauty of this bridge. So whoever has thought of this bridge, he might be a genius. Okay, so he has ignored, or he is able to mitigate the effect of all contact resistances by this intelligent connection. You see, this is not a new scientific discovery. This is nothing like E equal to mc square, but this is an intelligent connection of wires so that these contact resistances are carefully avoided. Okay, so this is the beauty of this engineering. Let me conclude this class just by mentioning one small observation about this circuit. So if you look at this circuit, okay, so if you look at this circuit, so one small observation, these two resistances A and B, they are actually dividing this contact resistance C in the same proportion as A and B. Why? Let us see here. So after this delta to star conversion, the resistance which is here on the left side is AC by A plus B by C, and this side is BC by A plus B by C. And so it's like it's dividing this resistance C, this was C, so this C is divided in the ratio of A by B. So if you take the ratio of these two, just take the ratio of these two, so see that this ratio AC by A plus B plus C is to this BC by A plus B plus C. This is nothing but A is to B, which is same as P is to Q. Okay. So in a sense, this extra this is the second bridge. This is why it's called double bridge. It has one bridge like this Wheatstone bridge and another double second bridge which is dividing. So this AB is dividing this contact resistance in the same ratio as A is to B. So this part is becoming proportional to A and this part is becoming proportional to B. So this is like a I often call it a resistance divider. This is my terminology. Like we have potential divider, this is like a resistance divider. So this is dividing this contact resistance C in the same ratio as A is to B, and therefore even in the balance condition P by Q R by S, same equation is holding true, because this extra resistance which is due to the contacts terminals, which can get either added to R or S, but this is being divided in the same proportion as R and S, therefore the balance equation is not changed. Okay, so this is like a resistance divider. Thank you.